So now we have the pleasure of looking at our final new section of material for the semester. We're in chapter 11, Goodness of Fit and Contingency Tables. There are two sections in this chapter. Section 1, Goodness of Fit, we discussed last time. And in section 2, our final section for the chapter and for the semester, we're going to look at contingency tables. So key concept. We now consider methods for analyzing contingency tables, which include frequency counts for categorical data arranged in a 2x2 table. We present a method for conducting a hypothesis test of the null hypothesis, that the row and column variables are independent of each other. It says we'll also consider 3 variations of this basic method: homogeneity test for homogeneity, Fisher's exact test, and the McNamar's test for matched pairs. But the basic method here involves looking for independence between 2 variables. So we discussed in chapter 9 a little bit about when data that we collected was collected dependently or independently, and whether we had matched pairs. And we looked also in chapter 10 at the idea whether there was a correlation between 2 different variables, specifically about a linear correlation that could lead to linear regression. But sometimes we observed there was a non-linear correlation. And so in this case, we tackle the general idea about whether 2 variables are dependent or independent, meaning whether changes in values of one seems to have an impact on changes of values of the others. And this is not causational. This didn't mean that changing one caused the other thing to happen, but whether there seems to be some dependence that they both rise or fall together or vice versa, something like that. And so the example that we looked at early on in the class is you might observe that you might see that observed ice cream sales rise, and that there seems to be a correspondence between the fact that also there's a rise in observed drowning deaths. And so that these end up being viewed as dependent variables, that there's a correlation. Now, this doesn't necessarily mean that it's eating more ice cream that causes more people to drown, but somehow there's a dependence between these 2, that if one is going up, that suggests to you the other might be going up. And how can that happen when there isn't causational relationship directly between the 2? Well, there can be hidden variables involved. So for the example, with ice cream consumption and drowning deaths going up, it's that often they both go up when the weather gets hot. More people swim, and therefore there's more observed drowning cases, and more people eat ice cream in hot weather. And so just the fact that both of those things occur more frequently means that there's a dependence between them, but they're both dependent on the fact that they're temperature sensitive in terms of increases and decreases, things like that. All right, so just pointing out that dependency and correlation and causation are subtly different things. So we're really going to focus on this idea of conducting a hypothesis test that variables are independent of each other, that they don't seem to rise or fall together in any way. All right, so let's look more closely at the idea of a contingency table. A contingency table or two-way frequency table is a table consisting of frequency counts of categorical data. Categorical meaning just like yes or no, male, female, favorite color, categorical data, corresponding to 2 different variables. One variable is used to categorize rows, and a second is used to categorize columns. All right, so let's right away, because they're going to jump into letters and do all kinds of things in formulas. Let's see if we can think about this a little bit with a simple example. So I'm going to make a table. And let's say my first categorical value that I'm going to separate in columns. And I'm going to just classify whether a person is a vegetarian or not. So I'm gonna, in these columns, if someone's a vegetarian, they go into the vegetarian column. If they're not, they go into the not column, not a vegetarian. And then in the rows, I'm gonna have another categorical separation of the data in which I'm going to put whether someone's car is a convertible or not. So then what goes, once you've defined the categories in rows and columns, then the cells themselves will consist of frequency counts of the categorical data corresponding to the two different variables. So let's say I look at 100 different people and their cars. As they drive into DVC, I talk to them, I look at their car. And I ask them, are they a vegetarian or not? And I look at their car and see if it's a convertible or not. So let's say out of that 100 people, let's say that 40 of them were vegetarians. So that means my vegetarian column would have a total of 40 people in it. And of those, let's say that 10 of them were driving convertibles and 30 were not. So there's my 40 vegetarians. 10 were driving convertibles and 40 were not. Then let's say I looked at all of the people who said they were not vegetarians. If I talked to 100 people, that would be the other 60. And so then I looked at them and see which one drives convertibles and which one were not. So let's say in that one that 30 were driving convertibles and the other 30 were not. So I have a bunch of frequency counts with a total of 100 observed items broken into these two variable categories, vegetarian or not, convertible or not. This is an example of a contingency table. Okay, so this kind of a thing, a contingency table, allows us to have a sample of observed values that we can use to test a claim about whether being a vegetarian or not is independent of whether you drive a convertible or not. Whether those variables are independent from each other and one has nothing to do with the other, or whether there's some dependence between the two and that one seems to rise or fall or has a change in value of one has an impact of the change of value of the other. Okay, so this is a contingency table. So this test of independence that I was just discussing, in a test of independence, we test the null hypothesis that in a contingency table, the row and column variables are independent. There's no dependency between the row variable and the column variable. So if we're looking at my little table here, the idea would be if whether you're a vegetarian or not has no dependency on whether you drive a convertible or not, or vice versa, then you would kind of think that whatever the split in the population is between vegetarians and not vegetarians would pass along equally to convertible drivers and non-convertible drivers. So in my example here, there were 40 out of 100 that were vegetarians and 60 that were not. So 40% of all of the people were vegetarians. So if that's the case, you would think that then most often, if you took a sample of and looked at whether they were convertible drivers or not, that whether you got a vegetarian or not wouldn't change the ratio of convertible drivers to non-convertible drivers in terms of whether you have a vegetarian or not. So for example, if I look at, if 40% of the folks are vegetarians and I look at all the convertible drivers that I picked, well, then I would think 40% of them would be convertible drivers. And it was 10 out of 40 in this case, which is only 25%, kind of far from 40. So there is a discrepancy there. So in the previous section, we looked at the idea of expected values compared to observed values. The same thing is going to go on here, but it's a little bit more complicated in terms of what the expected values might be, and we're going to let StatCrunch do a lot more of that work for us, even though they'll provide us for a formula here. But basically we can look at a contingency table and see if there was no difference, no connection, no dependence between the two, then we can see in the table whether that bears out or not, or whether the differences in our observed values shown in the table really make us think that whether you're a vegetarian or not seems to be dependent on whether you're a convertible driver or not, or vice versa. So that's the idea of a test of independence, with a silly example to think about. Okay. So the objective, to be able to conduct a hypothesis test of independence between the row and the variable and the column variable in a contingency table. And so we're going to have some notations. O represents the observed frequency in each cell of a contingency table. So those numbers here were what I observed: 10 vegetarians in a convertible, 30 non-vegetarians in a convertible, etc. Those are all O values. E represents the expected frequency in a cell found by assuming that the variables are independent of each other. So if I looked at 100 people, there is some expectation of how those would be divvied out if really the two variables had nothing to do with each other. And so that E, they're going to give us a little formula for that. StatCrunch is going to do that for us. But we can then sort of see, did the results, if there was no dependence, match up with what I would expect? Do the observations match up with expectations if they are independent? So what you can imagine is if you are assuming they're independent and you have some expected things you would see, and what you observe is very different from that, and would be very unlikely to occur by random chance, then you can say, well, what I saw in my sample is evidence to reject the idea that they're independent and instead support the idea there's some dependence between these. And you may recall that when we're looking at how big of a difference there are between things, that's typically a chi-square distribution. And we saw a chi-square distribution in 11.1, and we now will also see a chi-square distribution in 11.2 when we are comparing observed values to what we expected to see. Now we have an R for the number of rows and C for the number of columns in a 2x2 table. Those are both 2, but you might have bigger examples that we're working with where where R or C might get larger. So as usual, to use these numerical methods for these distributions, we need to have some requirements fulfilled for the math to make sense and be valid. As always, the sample data need to be randomly selected because biased data leads to biased results. The sample data are represented as frequency counts in a two-way table with the two different variables being displayed in the counts, because that's the kind of analysis we're doing. And it says for every cell in the contingency table, the expected frequency is at least 5. So we've had this kind of requirement before. The basic idea is that if you're trying to test a theory that leads to expected values, you need to have enough observations in your sample so that every single thing you are looking to see if the expectations were met is accounted for well enough so that we can test it. And that means that every category you're thinking of, you should expect to see at least 5 in order to test the theory that your expectations are correct. Because if you say, well, I only expected to see 1 and you don't, well, that's hard to see whether your expectations were wrong or just that it happened randomly because you expected to see so few. But if you expect to see a minimum of 5, even in the rarest of your categories, and then they don't show up, well, then maybe there's an argument against your expectations being correct. So we need an expectation of at least 5, not the observed values, because the observed values may turn out to be nothing, and that shows your expectations were wrong. But with expectations of at least 5, then zeroing out observed values provides helpful information. And so observed values will just be whatever they are. But for the math to work, we need the expected values to be at least 5 in each cell. All right, so those are the requirements. And as usual, for a hypothesis test, we need a null and alternative hypothesis. In this case, you can think of the null hypothesis has always meant equality for us, so that you can think that if these were independent variables, then sort of which answer you get when you have one variable switching to the other is sort of, if they're independent, they're equally likely. Like I'm equally likely to get a vegetarian when they're in a convertible versus not in a convertible. If those are equally likely, that's because those variables are independent and one's not affecting the other. So that's kind of why it's like the independence is like equality, because it's an equally likely kind of occurrence. But this will always be the case. So you can also just remember, anytime you have the null hypothesis, you're talking about independence. And then the alternative to that is that the variables are somehow have a dependency, they're dependent. That's by the default. So they do give us a formula. And again, we'll let StatCrunch do this for us, but we can see we have a chi-square distribution. And you can also see that you're looking at squares of differences between observed values and what you expected to see. And that's the idea, that the chi-square distribution measures how far apart what your sample got from what you thought you would get. And that's kind of the idea by the chi-square distribution in general. Now, they do have a formula for getting an expected value, and I could explain it, but students never seem to feel that helped them. So let's just go with what it says and the fact that those expected values can be looked at or demonstrated, but StatCrunch is going to do the work for us. All right, so let's skip through this formula stuff. P-values are typically provided by technology. That's going to be our go-to method. But a range of p-values can be found from that table that we hopefully never use at this point. So critical values, remember, we could be using a p-value method or a critical value method. And since this is a chi-square distribution, which is always a right-tailed test, basically, for the chi-squared, whether there's enough difference or not, degrees of freedom matter. So you may recall for the chi-square distribution, degrees of freedom matter. So degrees of freedom in this case is the number of rows minus 1 times the number of columns minus 1. So in a 2x2 table, the 2 and the 2 would both get subtracted and get 1 by 1, and you'd get 1 times 1 is 1. So that's very low degrees of freedom. But if you have more categories, the degrees of freedom may rise. Now, of course, StatCrunch also will just tell you what the degrees of freedom are if you have a contingency table and you put it into StatCrunch. But the critical value method would be on a chi-squared calculator. If you needed to say, remember, the critical value is the test statistic you need to hit in order to have the test fail to reject the null based on your significance level. And so the critical value is what test statistic do you need to surpass to reject the null. So it's only based on your alpha level. And so for that reason, we use the chi-squared calculator to get that. But again, they'll often provide you with the critical values table for the chi-squared distribution in the problem if you need to use it. And then if you do that, you don't need to use the calculator in StatCrunch. So here's the two basic logical ideas of how you're going to assess a hypothesis test for independence. And so independence would mean that the difference in expected values doesn't change when you change in one category in one variable to the other. And the chi-square distribution measures the difference with the expectation of equality. And so when the chi-squared value is small, that means there wasn't much of a difference when you switch from one variable to the other. That means that if you're assuming there is no difference, that could happen very likely. That's a very high probability, large p-value when the x squared value is small. When chi-squared is small, you have a large p-value, a large probability that there's really no dependency here, and that any differences you're seeing from the row versus the columns just occurred by chance. High p-value of that. So when you have that large p-value, you fail to reject the null, which is the null is going to be an assumption of independence. And if you can't reject that, that means there's insufficient evidence to claim that the variables are dependent and that they're probably just independent. Whereas in the other direction, if them being independent and not having much of a change from row to column expectations, if when you make observations, you see a very large difference from that expectation, that will lead to a large chi-squared value. And that would be very unlikely to have occurred just by random chance. So the p-value will end up being lower. And as we normally say, if the p is low, the null must go. The null is independence in this case. So for contingency tables, if the p is low, independence must go. And we reject the null hypothesis of independence, and the sample shows evidence in support that the variables are dependent. So that's kind of the split logic that we're using when we're comparing the observed values with the corresponding expected values in a contingency table test. So if the p is low, independence must go for our p-value approach. So now we've gotten an example to help illustrate this with 4 slides. The table on the next slide is a contingency table with 4 rows and 2 columns. The cells of the table contain frequency counts. The frequency counts are the observed values, and the expected values are shown in parentheses. So they've gone ahead and calculated expected values. Again, the expected values are assuming the variables are independent. Then this is what we would expect. Assuming the values are independent, what would we expect to get? And then we can compare that to what they actually got. And they've calculated all those expected values for us with that little formula. The row variable identifies the treatment used for stress fracture in a foot bone. So somebody breaks a bone in their foot and they receive some kind of a treatment. And the kinds of treatment they got are the row variable. And the column variable identifies the outcomes as a success or failure. And then we refer to the table to find the expected frequencies for the cell in the first row, first column. So let's take a look at the table. So in this table, here's our different surgery, weight-bearing cast, non-weight-bearing cast for 6 weeks, non-weight-bearing cast for less than 6 weeks. So these was the method of treatment used to help somebody who had a broken bone in their foot. And then in this other column here, the columns define whether there was success or not. The rows define type of treatment, and the columns define success or not. So what are we looking to see here? We're looking to see if success or failure of the treatment to help fix the broken bone is independent of the kind of treatment that they got. Do any of these work particularly better than any of the others? If some of these methods have a better success rate, that might suggest that they have an impact on whether your treatment is successful or not, and maybe you should do those more frequently. If none of these really seem to matter as to whether you have success or failure in treating your broken bone in your foot, well, then maybe you don't want to necessarily use the most expensive one, for example. So it's a very interesting question as to whether the type of treatment you get has some dependency on whether there's success or failure or not in the treatment itself. All right, so the E in each cell is what we would expect to see with the amount of people that were sampled here if the type of treatment had no dependence on success or failure, or vice versa. If success or failure, I should say, had no dependence on what type of treatment you got. If that were the case, then we would expect that the surgery would have, when it looks like they did a total of 54 plus 12 are in the surgery row, so that's 66. So 66 people were given surgery. And so if the fact that you got surgery didn't increase or decrease your success or failure, then we would expect that 47 of the surgeries would have successful results, and 18 and a half on average would have less, would have failed. And what we see is actually that there were more successes than that and less failures in the surgery. Now, is that enough to be something different than random chance? I don't know. We'll have to test that. So that's the idea of what's going on in this example. So they show their little formula for how they got the expected value in the cell, and we'll just pass that over. But then they have an interpretation. It says we can interpret the expected value by stating that if we assume success is independent of treatment, then we expect to find the 47 versus the success for the surgery versus the 18, I think, was for non-success. There's a discrepancy between the fact that we observed 54 successes with the surgical treatment versus an expected 47, 48 kind of number. And such discrepancies are key components of the test statistic that is a collective measure of the overall disagreement between what we saw and what we thought we would get based on our assumption that the variables are independent. That sets up the chi-square distribution. The chi-square distribution will then measure how big that discrepancy was so that we could draw a conclusion about whether we think the variables are dependent or independent. So this first 4 slides just focuses on the idea of a contingency table and observations compared to expected values. So with that comparison in mind, we could say, does the choice of treatment for a fracture affect success? And now there's another 9 slides to push forward with the idea of how we would test that. It says, use the same sample from the previous example with a 5% significance level to test the claim that success of the treatment is independent of the type of treatment. Surgery, cast, doesn't matter. Your success for treating your broken bone will be the same no matter what treatment. That is the claim. What does the result indicate about the increasing trend to use surgery? So it might be that if it really didn't matter which treatment you got, that doing more and more surgeries, which are much more expensive than just sticking a cast on somebody, is not really warranted because they're a lot more expensive, much, much, much more expensive. Whereas if the surgery shows a much higher rate of success, well, then maybe we shouldn't be worrying about money when we have a type of treatment that is better for people, and we should increase that type of treatment because it has a higher rate of success. Those are sort of the arguments involved, but the test just tells us dependent or independent. What do you think? 8 more slides in this example. So with that in mind, first, as usual, they would check requirements on the basis of the study description. We'll treat the subjects as being randomly selected so that they're not biased in some way. The results are expressed as frequency counts, which is a requirement to have a frequency table, a contingency table. And as we saw in the e-values that they showed us, they were all at least 5. The lowest expected frequency was 6, over 6. Now, if we go back to the table, there was an observed failures of non-weight-bearing casts for 6 weeks that was only 3. So this illustrates that the observed values don't have to be at least 5. But that instead, the expected values need to be at least 5. The lowest expected frequency was 6.1, whereas one of our lowest observed values is actually 5, but that's not what you check for this requirement. So that's satisfied. So the null hypothesis will always be that the variables are independent. In this case, success is independent of the treatment. And the alternate hypothesis is that there's some dependence, that success and the treatment that you get are dependent. And we're using a significance level of 5% to test that. So they crunched some stuff in their formulas and got a chi-squared value of 58. StatCrunch will do that work for us. And anytime they have these big formulas with some dots in the middle, meaning they had to do this a bunch of times, and we're like, oh my God, StatCrunch, save us. So StatCrunch would also give us this. So 58. So that's actually a pretty big chi-squared value. If you remember any of your previous work with the chi-squared distribution, That's a pretty big value. That probably means a pretty low p-value. That probably means that there's enough of a difference with what we observed to suggest, compared to the expected values, to suggest that the variables are dependent on each other. P-value, so it says, well, for p-value, we're not going to use a formula, we'd use technology, and they show Excel stat. And they show, and there's that chi-squared score. And notice the p-value was nice and teeny. And in this case, on Excel stat, they even show the critical value, which depends only on alpha. We could get the critical value in StatCrunch using the chi-squared calculator and the significance level of 5%. But the chi-squared value that we observed, this 58 thing, is definitely beyond the critical value. And the p-value is definitely lower than the significance level. So the p-value, now they do show degrees of freedom. As I mentioned before, it's the 1 less than the rows times 1 less than the columns multiplied together. But again, StatCrunch will do that for you as well. But the p-value is below the significance level of 5%. That's not 5%. So they're saying it's below 5 thousandths. And so therefore, there it is. The p-value is less than the significance level of 5%. There's the significance level. So p-value is very small. So we reject the null hypothesis of independence. Using the critical value method, the critical value displayed by the technology came out to be 7.8. And the actual test statistic was like 58. So that's beyond the critical value in the critical region, and therefore we would reject the null. So this little diagram says our critical region is defined here by the critical value. That's where an alpha is equal to 5%, meaning that 5% of the area is to the right of that point. And so since the test statistic was way over here, that means you were way off in the critical region. There's much less than a 5% chance that this would have happened if the variables were independent. And since the p is low, we reject the idea that the variables are independent and say that they're dependent. The evidence supports that they're dependent. So that'll be our conclusion for our interpretation. It appears that success is dependent on the treatment. Although the results of this test do not tell us which treatment is best, it just says that it does affect whether you have success or not. And it says, just as a follow-up or an afterthought, we can see the success rates of 81%, 44, 96%, 77 suggest that the best treatment, which was that one with the highest success rate, is a non-weight-bearing cast for 6 weeks, not surgery. These results suggest that increasing use of surgery is a treatment strategy that is not supported by the evidence, because even though it's got a higher rate than maybe some of the alternatives, it doesn't have the best rate, and you should more often increase the treatment to match the best chance of success, since there does seem to be a dependence on success to what type of treatment was used. Okay, so now we're looking at problem number 23 on our homework number 14 from chapter 11. So this is on 11.2. It says a study of seatbelt users and non-users yielded the randomly selected sample data summarized in the accompanying table, and there's a link to it here. Use a 5% significance level to test the claim that the amount of smoking is independent of seat belt use. So whether smokers, it says here, a plausible theory is that people who smoke less are concerned about their health and safety and are therefore less concerned about their health and safety. Oh, I'm misreading this. A plausible theory is that people who smoke, comma, are less concerned about their health and safety and therefore less inclined to wear seatbelts. Is this theory supported by the sample data? So the theory would show a discrepancy and we could see which was bigger, but we're going to set up our contingency table hypothesis test on just whether there's some dependency between smoking and wearing seatbelt use. And then we could look and see if the smokers wear it less or not in further support of that theory. So to set up the null and alternative hypothesis, the null hypothesis is always for independence between the variables, and the alternative is always for dependence or not independent. So looking at A, it says the amount of smoking is dependent upon seatbelt use. That's not the null, that's the alternative. Looking at B, the amount of smoking is independent of seatbelt use. That sounds right. The amount of smoking is not independent of seatbelt use. So it looks like it's B. I'm not reading the rest of it. So then they want the test statistic. So now let's look at this table and see here that we have number of cigarettes smoked per day, and they have it into whether they smoke 0 and then more or more or more. And so you would think, if this plausible theory was right, that as the smoking went up and up and up, they're less and less and less concerned about their health or safety, and they would wear seatbelts on average less and less and less the more they smoke. That's the theory. We're just going to try to see if these are somehow dependent on each other or not. So let's dump this over into StatCrunch. And so when we open this in StatCrunch, what we can see is that across the top row bar are the labels for the columns about smoking amount. And then the first column labeled variable 1 is actually about the variable choice, whether they wear a seatbelt or not. So to perform this hypothesis test, or to get our test statistic for the chi-square distribution, this is a contingency table. So I'm going to go to Stat, and I have to go to Tables, Contingency, and anytime it's summarized in a table, that's going to be with summary. So then this big tool comes up, and in this tool, we need to tell the tool which columns have the observations in them. See if I can get out off of this highlighting. There we go. And the columns with the observations are these columns here, the ones with the cigarette things listed, but it's those titles. So I need to move all of the columns with observations over to the right. So the first one is the cigarette one. And if I hit Shift, I think I can grab the rest and move those all over. So those are the 4 columns with the observations in them. And then the row labels are in this first column, which has on the top of it variable 1. So I select the variable 1 column because that's where the row labels are about whether they wore their seatbelt or not. Now we're doing a chi-squared test for the independence between the variables, and that's the default chosen here. So let's compute. And we get this sort of repetition of the table, but the nice thing is they add a little bit. They show us the totals for each row, the totals for each column, the total number of observations all together. That's kind of helpful. Degrees of freedom is here. They tell us this is a chi-squared statistic. And then they give us the chi-squared value and the p-value. Now, they're asking for the test statistic. So that's going to be the value of the chi-squared to 3 decimal places, looks like there. Need to round the 2 up to a 3. Then the p-value to 3 decimal places would be cut off at the 1 there. No change needed. And now we're supposed to draw some sort of a conclusion. Well, the simplest way usually is to use the p-value method. If the p is low, independence must go. Well, the p is not low. It's like 60%. It's definitely not below our 5% significance level. So that means we cannot reject the idea that they're independent. There's insufficient evidence to do that. So we fail to reject the null. So which of these tells us that that's what we're going to conclude? There is not sufficient evidence. That's true. There was not sufficient evidence for something to reject the claim that the amount of smoking is independent. that would have been what we would reject if P was low. So there's not sufficient evidence to reject that they're independent. The theory is not supported by the sample data. That looks right. I haven't read the others yet, but that looks right. Let's go ahead and take a look at the others real quick. There is sufficient evidence? No. When the P is not low, this could have happened by chance, and that's not evidence of anything. So we're never going to conclude that there's sufficient evidence when you have a high P value. So the other choice that has not sufficient is C. There is not sufficient evidence to reject the claim that heavy smokers are less likely. No, the claim we would be rejecting is the null hypothesis, not the dependence. So A is the right choice.